Hi, my name is Audrey Garon, and I'm in Professor Roberto Tron's Mechanical Engineering Lab. So it's easy to order toothpaste on Amazon. All you have to do is click buy, and it shows up to your house within a few days. But behind the scenes, on the factory floor, robots and humans work side by side to make sure that your toothpaste gets put in the right box with the right shipping label, all so that you can have clean teeth. But what happens if that robot is hacked? Now, precious items such as your toothpaste are at risk, along with everything else in the factory. The Tron lab found that robots can monitor one another by using their sensors, such as video cameras, to compare their observations with where they expect the other robots to be. But in order for these robots to actually be able to detect other robots within their video feeds, a neural network is required. My project focused on building a convolutional neural network, which is just a type of neural network, which labeled images based on whether or not they had a Roomba create robot in them. Neural networks mimic human decision making through a multi-step process in which data inputs are transformed by nonlinear and linear functions to produce an output. And the parameters of these functions are learned to maximize the accuracy on a training data set. But before I get ahead of myself, a neural network sounds really complicated, right? A data set is required. So I first built that using both positive and negative examples. So my positive examples included images that contained the robot, and my negative examples had just random spaces around the lab. But a challenge of neural networks is that they require a really large data set. So I used a procedure called data augmentation to make a bigger data set by, for example, swapping the green screen background of these images with other images, and I also vertically flipped the images to make a bigger data set that contained over 1,000 images, whereas before they only had about 500. I also wanted to further challenge the model because initially when I ran the testing data set through the neural network, I got an accuracy of 100%, which is not by any means practical. So I challenged the model by writing a script that randomly turned pixels in the testing data set black, which challenged the model, and the accuracy decreased from about 99% to 17% as I increased the number of black pixels. In real-world security issues, this convolutional neural network that I programmed can be used for robots to compare their observations with where they expect the other robots to be.